go with buckling. Columns you're going to do, and then first one in that, buckling and stability. Am following Timoshenko textbook. Timoshenko. Always you have to hold one textbook and read Timoshenko. Okay. So let us see. See, buckling actually is about bending itself. Buckling of column is closely related to bending. Okay. What is that? Let us see. See, in fact, if I have a say straight buried customer, this is a slender column which is held by a roller support. Okay, roller support and you don't have to do anything. Okay, this is also a slender, not very slender. Okay, this can be slender. Also, this is not very slender, but if you take still more slender, so if you put a pressure on this, what's going to happen? If you solve the equations, if you solve the equilibrium equations, then it is in equilibrium. Whatever you put force, nothing is going to happen. But then this is one particular case where we are talking about stability. This is one of the main thing. First thing, what we are talking about stability. What can disturbance do? For example, when you're putting it straight and you're increasing it, it's okay. But sometimes if you shiver, then there is something called perturbation. Perturbation is small changes. And a small axial change you have, then what may happen? It may see, first of all, there is bending. The perturbation can happen also because there is a small load which is there here, which causes the bending moment. I will tell you one by one how the bending moment is caused here. And that bending moment, if there is a force that opposes that bending moment, fine. But above a particular critical load, it cannot oppose the bending moment. The what do you call, the whole column will continuously go. It will buckle at once. It may, when you talk about buckling, it might be cutting also, fracture also. ಒಂದು ಇಡಿಸುಡಿ ಕಡ್ಡಿ ಇಟ್ಕೊಂಡು ಅದರ ಮೇಲೆ ಇದು ಹಾಕಿದ್ರೆ ಇಡಿಸುಡಿ ಕಡ್ಡಿ ಏನಾಗುತ್ತೆ? ಇಡಿಸುಡಿ ಕಡ್ಡಿ ಅಂತ ಗೊತ್ತಲ್ಲ? ಇಡಿಸುಡಿ ಕಡ್ಡಿ ಅಂದ್ರೆ ನಮ್ಮ ಇದಕ್ಕೆ coconut broomstick. A broomstick you take and you put a load on that, what is going to happen? It is going to buckle, it will bend, and at once it is going to buckle. It's going to cut. There might be some other way of having it. It will have permanent damage. It will not come back. It goes like permanent damage. Then it will not come back. It has buckled. Makes sense? These kind of things. Plastic deformation will happen. Okay, and sometimes plastic deformation like water flows, such kind of things may come, and it may not come back. These are all the cases of buckling. There are different types of buckling which is there, but a simple one, let us understand. So what happens? This one, if it is there, it, because of the load which is being put, it may, because of the compressive load being put on the, say, compressive load of the air. This is not going to. Okay. So let a compressive load P act on this thing, and this is a surface. So because of this, what happens, because of the load, it moves down, and there is a buckling which happens. There might be elongation also. It may buckle because of the load being applied. Okay, so that is how it is. Okay, now this is because of axial compressive load, is it not? Okay, so here, okay, a slender member, a slender structural member subjected subjected to axial compressive load, axial compressive load may fail may fail due to bending 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 rather than rather than because of axial load axial load, then such kind of failure is called bending. Sorry, is called buckling. Very important. What happens? It does not fail because of axial load, okay, but rather fail due to bending rather than because of axial load. And such kind of failure is called buckling. Very easy. Correct. Slender is thin. Slender is very thin. Exactly. Compared to height is very high. Okay. Slender means slender means the cross sectional dimensions are small compared with compared with longitudinal dimensions. Cross sectional dimensions or lateral dimension. Lateral dimensions are small compared with longitudinal longitudinal dimensions. Now, what is slender, how much it should be, and all those things varies from one case to the other. Okay. Now, let us understand this buckling in terms of spring and mass. Okay, spring in terms of spring stiffness. Done. No, start. Done. Now, next point is let us understand. Let us say, not finished. Finished. Now, let us say that see here understanding is very important. Let us take a case of a slender, not slender, a bar like this. Let there be a bar, okay, which is connected to a spring of stiffness beta and the load P is applied. Okay, let this be point A, let this be point B. As the load is applied, it may so happen that it may get deflected. It may get deflected due to some disturbance. Yes, please. Huh? Hinged everywhere. This is hinged. Okay, this is hinged, not fixed. Okay, whenever we put it like that, it is hinged. Okay, so let us put it directly to where we know it is hinged. Hinged. Okay, and here also hinged. So it's hinged support. Okay, so here also it's hinged support. There's hinge here. Okay, great. It is not fixed. Here it can be fixed. Yes, it can be fixed, or it can be, yeah, it can be fixed also. It can be hinged also. Okay, yeah, it can. Sorry, here if it's fixed, it's not right. I'm very sorry. Here it can. It better we put it hinged also. Change students if you're written with pencil. Change. If it is fixed, what happens? The buckling will happen with fixed load also. So if you have that, there's no problem at all. But only thing is that you have to write the slope here as straight. That's it. If it is hinged, I can have a slope here. I can have a slope here because it's hinged. If it is fixed, then you have to do it like this. This is how buckling will happen if it is a fixed load. That's it. It will not go. It will go like this. This is the fixed load bending hinge buckling. Okay, just like other different types of support conditions can be there. So if that time it is there, it's no problem at all. Don't worry. Okay. So once it has failed, we cannot say anything about it. Okay. So it's beta. So this is a beta which increases in its size, and there is a force which is applied by the spring on this direction. Okay, let us say. Okay. So now what happens is, see, let us say that AB is a rigid bar. Let AB be a rigid bar, be a rigid bar. So nothing is there. It cannot. It's a rigid. Rigid is rigid. Okay, and that is pinned at the base. That is pinned at the base. That is pinned at the base, and that is pinned at the base and supported by an elastic spring, by an elastic spring spring of stiffness beta. I'm explaining. Wait, there is a force which is added here. There's no self weight, nothing. Okay, here it is P. Okay, that's correct. Stiffness beta. Stiffness beta. At the top, let there be something at the top. Okay, so stiffness is also called a spring constant, right? The bar supports the supports bar supports a centrally the bar supports a centrally applied load P that is perfectly aligned, that is perfectly aligned that's perfectly aligned with the axis of the bar, with the axis of the bar, that is perfectly aligned to the axis of the bar. Hence hence the spring has the spring has no initial force, no initial force in the force in it, no initial force in it. Now suppose that now suppose that the bar the bar is disturbed by some external force, some external force, such that such that the bar rotates slightly, bar rotates slightly through a small angle theta, theta about support A, about support A. So it rotates by a small angle, which is theta. It is rotated by a small angle, okay, by small angle theta. It has rotated. Okay. Now, once it is disturbed, what is that controls the whether it goes till the end, large deformation, or it has small deformation? What does it control? What is controlled? P, the load P decides whether it will have a bigger deflection or a smaller deflection. If small p is acting, if a small p is acting, then what happens? It will stay there and it will not come back. Sorry, when this is removed, it will come back. Whereas if you put a large force, what will happen? It will go on increasing till when it reaches down. It will have failure there. So what happens? There will be a critical P. There is a critical P for which it continuously deforms, and there's a critical P when you remove it comes back. Critical P below which, a critical P below which it will come back. If it's more than that, it will continue deforming. So we have to find out that P critical. That's it now. That is our main purpose. Is it? So let us do that. Okay. You hope I got the. I hope you got this point. Okay. I don't know. It's just full of fumbling. Okay. Finish, Mr. Don't wait for me to write fully. You write it along with me. Okay. It's explanation in that particular notes only. I'm explaining. Right. So you, because of P, we are using all this very slowly happening. Okay. So it's not sudden things. Here all are gradually loading. If the P is coming, also it comes slowly. So that acceleration is not important. Yeah, here at spring, we are illustrating the mechanism. Now, such mechanisms, when it is bending, what is happening? The bending stiffness, what is there, That shows what is the stiffness of the spring. Instead of spring, what is that when it is buckling like this? It is a bending stiffness which is trying to hold it back. You understand? This is idealized. Got the point? Within buckling is actually due to bending, right? You should see some Kapil Sharma show. There is a thin fellow comes. You hold on him something. You understand that thin fellow? Have you seen that? I don't know. Okay. Or in comedy, Laurel and Hardy show, you can see. Okay. When somebody holds like this, a thin fellow, you hold. The fat fellow will stand like this. Okay. So similarly, same thing. Buckling, bending, yes. It buckles under pressure. Okay. So sometimes you see that. Okay. So when that see, when you understand basics here, you can relate to everything. You can relate to whatever you see. You'll see buckling there. You'll see all the concepts in reality. Is it not? Okay, chalo. Next. Now, what happens? Very important. Okay. If the force P is small, if the force P is small, if the force P is small, right? The bar spring, bar spring system, the bar spring system is stable. Bar spring system is stable and will return will return to its initial position, return to its initial position when the disturbing force is removed. When the disturbing force is removed. Correct. When the disturbing force is removed, it will come back to the original position. Right. But if the force P is very large, is very large, if the force P is very large, the bar will continue to rotate. The bar will continue to rotate, continue to rotate, and the system will collapse. And the system will collapse. Now, collapse means what do you mean by collapse? The spring may be cut, okay, or the bar may break. Something may happen. Okay, so system will collapse. Okay, system will collapse. Thus, thus, for a large force, for a large force, the system is unstable. Stable, the large force, the system is if the here it's a rigid bar. We are not talking of stiffness at all. Stiffness infinity. Huh? No stiffness in terms of what? Now you have to talk about system in terms of what? Axial compression. Okay. 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 We'll say we'll design in such a way the system is stable. Then. No, it is not. It's not. Springs you've seen, is it not in machine design? How is the springs? What is springs? What is the main? What is the main? See, if you have a spring, you have a coiled spring. If you have a coiled spring, and when you put a load on these two ends, what is the type of load which is happening on this individual spring? On that cross section, what type of load is added? No, No. When you have a coiled spring, when you put a load, what type of load is, what type of stresses are coming on that? Torsion. Yes or no? Have you not had it or not? Yeah, combination of bending or torsioning, but mainly is torsion. Torsion and bending both comes, is it not? Yes or no? When spring is down, when wound also, it is with the torsion that it is wound. And then a load is put. What happens? It rotates. That's why when you twist something, afterwards it becomes springy. Okay, so now what is the question? So it's not same as action compression. Okay, because it is torsion, everything comes into picture. Fine. Now what is your question? There is another question here. No. So this you have to take it as a rigid bar, very important. Rigid bar and a spring. Spring need not be coiled spring only. It can be a elastic bar. It can be a thin rubber band. Spring of stiffness. Here I have a rubber band. Okay, and it is coming like this. So it can be a rubber band. Okay, so you can think elastic bar means it can be anything, right? So system is unstable. Fine. System is unstable. And buckles. Buckles means fails. Buckles. Buckles. By undergoing large deformation. This is purposefully I am going slow, student, because this is one of the important things, and 2 mark comes in this, whether mechanical or civil. Okay, civil engineering is much more important, I think, in structural analysis. Is it not? Yes or no, Siddhi?
Yes, sir.
Yeah, it is very important in structural analysis and other things. So buckling is very important. So basics, if I'm clear, if you're clear in the basics, then whatever is further, whatever comes, that becomes very, very easy, students. Okay, so basics has to be clear. Okay, undergoing large deformation. Okay, so now, okay, undergoing large rotations of the bar, deformations, which is rotations of the bar, which is large rotations of the bar. Make sense? Okay. Now, now that is understood. Okay. For for now, when the bar, this is an example. This is, don't take this as buckling. This is an example to understand. Yes, this is an example to understand how the buckling works using simple one. Okay. It is not the actual buckling. Buckling will start. Okay, but we are understanding the mechanism of buckling. Okay. So now here, okay, when the bar is rotated slightly, is rotated slightly, when the bar is rotated slightly, the spring, the spring is elongated. The spring is elongated. Spring is elongated by an amount, by an amount, by an amount equal to theta into L. Correct? Where L is the length of the bar. Correct? You understand why it is theta into L, is it not? The corresponding spring force, the corresponding spring force F in the spring, F in the spring is F is equal to beta into theta into L, right? Let this be equation number 1. Okay, F is equal to beta into theta L. This force, this force creates a clockwise moment. So this moment, similar to this moment, is a moment which is acting in the when it is bending. So both things, there is equivalent. That's why I'm doing this all these things. Okay, not me. It's a pedagogy by Timoshenko. Okay, so if you say me, you don't think I have invented these kind of things. No, it's all the pedagogy. When people have invented these things, why not use it? Is it not? So and therefore that's why good books has to be referred. Okay, so clockwise moment. Okay, this force creates a clockwise movement about point A equal to F into L, right? Or or beta theta L square, correct? Okay. Beta theta L square. The tendency of the moment, the tendency of the moment is to bring back the tendency of the moment is to bring back the bar to its initial position, to its initial position, to its initial position, right? Okay. Hence, 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 beta theta L square is called the restoring moment. You should see the similar restoring moments in in the floating bodies. When there is a floating body, what will happen? The floating body, what is the restoring moment? It is the buoyancy force into the distance between G and M. Is it not? GM is very important. Yes or no? I don't remember. I just G and B. Is it not? G and B. Yeah, G and B. Yes, G and B. G and B. That distance is very important, right? So that restoring moment which is there is very important. Where it acts across the meta center. Very important. That meta center is a point where it acts. It's always in the floating bodies. B is always lower than G. If G becomes lower than B, then what happens? It's not stable at all. If G is lower than B, then what happens? Wait, wait a minute. Yeah, if G is lower, so G is always bigger than B, is it not? So buoyancy force, no. B is always bigger than G, is it not? So what is happening here? This is unstable, is it not? Okay, I'll see it later. Okay, I recall. See, that's why
B is below G, sir.
B is always below G, is it
Yes,
not?
depends upon how much it is submerged.
Yes, B is always below G. Okay, or can G go below B? Then what happens? It's always stable. It's always stable, is it not? The problem comes when B is greater than G. G is at a higher point, B is at a lower point. Then the problem comes. So what happens when it topples? Also, this is when it is a body
So
which
it
is,
depends upon meta center, no, sir?
yeah, it depends on the meta center. This is based on the body which is submerged. But when the body is, what do you say, floating, it depends on the meta center. So it is B here, G here if we have. So if it goes there with respect to the meta center, it goes here and there. Okay. So those things we will see later, but I want you to recall again. See, this is how it happens. Whenever you get a point when you're studying one thing, to recall the other one also. That time you'll not forget and you will connect. Okay, so that's very important. Okay, chalo. Done? Written down? No, right? Done. Next. Now here put a mind into understand it. Okay. The force P, the force P creates a counterclockwise creates. Write it along with me, students, so that we'll save time. Counterclockwise moment, counterclockwise moment about A that tends to overturn, that tends to overturn, that tends to overturn, overturn the bar, overturn the bar, thus causing a overturning moment, overturning moment, overturning moment, P theta into L. Correct. P theta into L. Exactly correct. P theta into L is the overturning moment, right? So now, if the restoring moment, if the restoring moment, which is beta theta L square, is greater than overturning moment, P theta L, then what happens? Then the system P theta L is greater than this one. Then the system is stable, is stable. It's not buckle. It's not buckling, right? Now, if B theta L square is less than P theta L, then system is unstable. System is unstable. Okay. Now, the transition, the transition from stable to unstable, transition from stable to unstable happens, happens at, happens when P theta L is equal to beta theta L square, which comes as theta cancels, L cancels, P is equal to beta into L, which can be called P critical, P critical, CR. P critical is called beta into L, right? P into critical, which is called, this you write it as equation number 2, which is the critical load. So there is a critical load above which it will buckle. Fine. Similar thing happens with the buckling of columns. Okay. So let us go with pinned joints. This is how it is. We have to find out like this one, right? So purpose is to find the load P for which it buckles. Right. So different types of loads are there. We will see one by one. What are those things? And here differential equations are important. Solving of differential equations is important. and here we will understand. Don't worry, everybody stay. Nani this, मैं हूँ ना, and all is well. ಸರಿ, ಆಯ್ತೇನ್ರಿ? ಈಗ ನೆಕ್ಸ್ಟ್, ಈಗ ರಿಯಲ್ ಬಕ್ಲಿಂಗ್ ಇದು ಈ ತರ ಮತ್ತೊಂದು read one page 553. Okay, read 553 of Timoshenko. Read page 553 of Timoshenko. When I say read, you have to read it, students. Okay, it is just he has said what is bifurcation, neutral equilibrium, and all those things. He has compared with a ball being there on a hill. Okay, so same thing. Okay, don't have to worry that you know, but still, if you read it once, it's better. Okay, so next. When that is there, it is neutral equilibrium, correct? And this is unstable, unstable equilibrium, stable equilibrium, and neutral. Same thing holds good here. Okay, so transition is called neutral. Right? Same thing. It's all theory of everything. Everywhere this is used. Now let us see column with pinned ends. Column with pinned ends. Later on we will see others. Pinned ends. So if you have column which has ends pinned, okay. So what is happening here? The column has the pinned end. So this is pinned here with the roller so that it will move downwards. And then I have a column, straight column here. Okay. And when it is pinned here, I also. And then here a load P is applied. Okay. Now we know because of some reasons, and this has a length L. See, this has a length L. Fine. Okay. Now what's going to happen? It's going to buckle sometimes, right? So let it buckle. Due to some reasons, it is buckling. What is the buckling happening? Because of bending, basically, right? So it's going like this, and it goes like this, and it goes here. It has a buckling load, correct? So what has happened here? It is P over here. It has been buckled. Okay. So now if I cut a portion over here, okay. So let us say this is the maximum deflection which is happening, which is considered as V. We have used V only previously, is it not, for the load which is there, right? Shear load, right? Not shear. Shear stresses we have used V. Deflection we have used V, is it not? That deflection, the movement we have used V. So the same. So we are using the same thing. And let us say this is direction X. This is direction X. And let us say this is direction Y. And this is direction Y. Fine. So now if I say the same thing over here like this. So let us say this is direction X, and then this is buckled here, this is buckled like this, and this being V, okay, and then here force is there, I'm sorry, this is V, and this can be the equivalent load P, and then the moment here M. So because of that there is a bending moment which is acting. Is it not? Without bending moment, how can it bend? Is it not? So that bending moment we have to see. Okay. So now we have to solve this equation. We have to solve this particular problem. Let us see how. Okay. See, it is known for us that it is known. It is known that that EI into d square V by dy square is equal to minus M. Correct? In the bending equation we have seen right? Remember this? Okay. So now further doing, this is equal to, now this can be equal to, so EI into d square V by dy square is equal to minus M, can also be written as minus P into V. The load applied into V, that is causing the moment. Okay, or further going, we can write this as EI into d square V by dy square plus PV is equal to 0. This is the differential equation we have to solve. This is the governing, this is the, this is the governing, or we will put it another way. Wait, okay. Let us write this. This is equation number. What's the last equation number we had? 2. Is it not? Let this be equation number 3. This is the governing differential equation for buckling. This is the governing differential equation for buckling. Now we have to solve it using the boundary conditions. That's it. Okay. We have to solve it and use the boundary conditions. See here, previously over here I missed one thing. Okay, let it be. I could have written one, this one, see here. In the previous one, I will write it. In the previous one, I can write a bifurcation diagram, something like this, where this side was beta, okay, see inside, okay. This side was beta, and this side was P, okay, beta and P. Now, if beta is much higher, okay, you can call this particular one as unstable equilibrium. This is unstable equilibrium. This is stable equilibrium. And this line is neutral equilibrium. Okay, that we will write it later. The same thing we will write here also. So neutral equilibrium when P is greater than P critical. This is P critical. This is a P line. This is a beta line. You understand? Not beta, theta line. I'm sorry, not beta, theta line. It varies based on P critical, depends on the beta. Okay. So was this one is actually P critical, which is equal to beta into L. Beta into L is this critical length or critical P critical, right? So this is P critical. This is called the bifurcation diagram. Higher the beta, that will rise. Lower the beta, it will come down. Fine. So write this somewhere, okay? And this is theta. Somewhere you can put it. Say this mental picture you have to create. Okay. When you are solving the problem, if you see as an equation, you will not be able to understand a lot. You have to understand in terms of diagrams. Okay, P critical. See, like Mohr circle. When you have Mohr circle in your mind, you see how easy it is. Calculating the different, calculating these, say, principal stresses. It's so easy when the Mohr circle is understood, right? So when diagram is there in your mind, the equation becomes easy. Okay. So you know when there is a compressive stress, equal compressive stress and equal tensile stress. Sorry, yeah, load which is one side compressive and one side tensile. You know what is the maximum shear stress, is it not? Yes or no? Yeah, one side 10 kilonewton compressive stress, one side 10 kilonewton tensile stress. What is the maximum shear stress? Forgot. Hey, where are you? Civil students, tell me. Huh? 10 kilonewton tensile stress on one side, 10 kilonewton compressive stress on the y-axis. On the x-axis, 10 kilonewton tensile stress. On the compressive, on the y-axis, it is 10 kilonewton compressive stress. Tell me what is the maximum shear stress? 10 kilonewton, is it not? Because you have a circle. On one side, there is one point, there is one point. Here you put a circle. So maximum shear stress is 10 kilonewton. So when you have it in your diagram, in your mind, the diagram is there, then it becomes easier, is it not? So that is one of the things. Okay, done. But right now, Sariya. Okay. Ega. Yes. Now this is the differential. Have you written this down? Right. Now once this differential equation is there for the pinned ends, okay, it need not be pinned ends. Generally, this happens irrespective of the pinned ends. General equation. Pinned ends are boundary conditions. Let us see. Huh? Dy square. Y is in this direction. See the y direction there. X is in the top direction. Fine. Sure. Everyone done? No. Right. Done. Next. Next. So I can write here. Okay. I can also write defining. If I define k square, or if I write it like this, okay, I'll write this as d square v by dy square plus p by ei into v is equal to 0. Taking p by ei is equal to k, we can write small k, small k. We can write, we can write k square, or p by k is equal to k square. Let us write it k square. Let us write it k square instead of k. I'm sorry, k square. Then we can write d square v by dy square plus k square v is equal to 0. Correct. Now we have to solve this differential equation, right? To solve this differential equation, what's the solution of this differential equation? Huh? Why? How can you separate the variables? You cannot. What is this? Homogeneous equation of second order with constant coefficients. Second order, it is of the order y double dash plus a y dash plus by is equal to 0. What you have to assume? We have to assume y is equal to e power ax. We have to assume, so that y dash would be a into e power ax, and y double dash would be a square into e power ax, or lambda x. Let us lambda x, lambda. lambda x, sorry, a only, I'm sorry, a only, I'm sorry. Lambda we will use lambda, so that way there's no confusion, and because a is there already here, so lambda square here, lambda, right? You're differentiating twice. Okay, the people who have not attended differential equation classes once into a small one here. Okay, so now you apply here, others it will be revision. Okay, so this is a side, I'm doing differential equation as one part only, small one. Okay, so this is how. Now you apply this here. So what is it? So y double dash, instead of y double dash, you're writing lambda square e power lambda x plus, instead of here a, you have a lambda e power lambda x plus b lambda square e power lambda x. I'm sorry, b into e power lambda x, correct? Y only is equal to 0. E power lambda x goes everywhere. So what remains? Lambda square plus a lambda plus b is equal to 0. Now you have to find lambda, that's it. So lambda is equal to lambda, there are two equations, the quadratic equation. So lambda 1 comma 2 is equal to plus or minus, sorry, minus a by 2 plus or minus square root of a square minus 4b divided by 2. How did we get that? We made the quadratic equation, we solved solution of the quadratic equation. So after we get that, we get lambda 1 and lambda 2. Solution is what? Solution is y is equal to c1 constant 1, sorry, constant c1 into e power lambda 1x plus c2 into lambda 2x if lambda 1 is not equal to lambda 2, is real, is real. Real means lambda 1 and lambda 2 are different and are real. That means it's not complex. Okay. Now y is equal to c1 e power lambda 1x plus c2x into e power, or c1 into x into lambda 1x if lambda 1 is equal to lambda 2, sorry, c2 only, c2 only, lambda 2x is real, correct? Okay, then this is the equation, there is a x here, distinct and real. So I have said lambda 1 is not equal to lambda 2. Different ways, different things are there. Okay, now y is equal to c1 sine lambda x plus c2 cos lambda x if lambda 1 and lambda 2 are complex. Make sense? Complex when it comes, when 4b is greater than a square. When 4b is greater than a square, it becomes complex. So when it is complex, it is c1 sine lambda x omega x. That omega we have to calculate. Yeah, we cannot do that, right? We have to consider that and we have to solve. Okay, let us see that. What is omega here? Omega comes as, so it will become as if a is 0. If a is not 0, then what happens? E power y is equal to e power, no lambda x here, a, no, we are taking a minus a by 2 x. So you take minus a by 2x c1 omega x. What is omega? Root of 4b minus a square by 4. Or this one, this comes as omega. When complex, it becomes 4b minus a square, right? Yes, omega square is actually, omega is equal to square root of 4b minus omega a square divided by 2. That has to be in the mind. Okay. Now here, what is the root? So let us root. Okay, see. So the characteristic equation, this you write it as 4 students. Okay, characteristic equation is this is 4b, this is 4a, right? Right, we are at 4, is it not? 3 is over. So characteristic equation is lambda square plus k square. Lambda ಇದೆಯಾ ಇಲ್ವಾ? ಇದೆ. Lambda is equal to 0. Now what it will be? What is value of lambda? Lambda is complex. Huh? Lambda square plus k square. Lambda square plus k square is equal to 0. Correct. Lambda square plus k square is equal to 0. Now if lambda square plus k square is equal to 0, what are the roots? Roots are complex. The roots are complex. So lambda 1 comma 2 is equal to e power lambda 1 lambda 2 is equal to, what is it, plus or minus ki. Correct. That means only this is there. B is not there. B is 0. Sorry, A is 0. A is 0. Only B is there. Observe here in this is missing over here. It's one of the very simple cases. ಇದೆಲ್ಲ ಮಾಡಿದೆಲ್ಲ ತುಂಬಾ complicated. ಇದು super simple. It's very simple. So it is plus or minus ki. Right. So what is omega? Omega is, what is omega? Omega is k only. Omega is k only. Is it not? Root of 4k. Right. So 4k square, is it not? This is k square, 4k square, so k only. So now what happens? This we have to substitute there. This is omega I. This is similar to having omega I. Makes sense? Write this thing here. Write this. What is the solution? Let us write it. And based on the solution, tomorrow we will have understanding. So we'll stop it here. I'll write the equation and then we'll stop. Okay, tomorrow we'll continue with this. So you don't have to worry about this. It will be so easy. It's very easy. Okay. Sure. Done. Next. Now, done? No, not done. 5 o'clock, 5:45 we will start zip transfer. And there we will start with our Vel Murugan sir. Pressure vessels is only for mechanical. For civil, thin cylinders is not. SOM is complete. SOM is complete. After this, next we will not have common topics. Common topics are done. No, what are the common topics now? Nothing. Partial differential equation is not a common topic. Complex numbers also is not a common topic. But I would encourage students to attend. That's it. You want to attend partial differential equations, so we'll have it. So what partial differential equations will be on timings when we have say pipe flow is done. That time we'll have partial differential equations. So 2 to 4 class will be 2 to 3:30 class will be only for civil engineers from now onwards until their specific civil engineering specific subjects is complete. This common slot will be converted to mechanical slot, or the other way around, here and there, because for them afterwards, no, this 2 to 4 itself is better for them, because yeah, what will happen is after that I will continue till 4, and from 4:30 to 6:30 I will take for mechanic. 5:45 they will start. Okay, so that would be better. Okay, so it will be extended after this. Either buckling is done, then from 2 to 3:30 what is there will continue till 2 to 4 for civil engineers, and for mechanical engineers it will be 4:30 to 6:30. Okay. Sure. So there will be increase in both the things. Okay, so here, what is the solution? The general solution. The general solution is given by V is equal to C1 sine kx plus C2 cos kx. What's the equation number? 5 is done. 6. Where C1 and C2 has to be found using boundary conditions. Has to be found using boundary condition. Done, students. That's it. Okay, so we'll stop it here. Okay. Huh? Yes, we are getting the particular solution for different types of this, different types of what do you call, different types of end points. The pinned points we will see first. Later on we will see others. Okay. Other support conditions we will see how it goes. Okay. Yeah, that's it. Then we'll go with eccentric loads. Okay. So we'll talk about radius of dilation and imperfections. So let us see how the things goes. Okay. Sure. Thank you, students. We took k square because here we will get k, is it not? Otherwise, what will happen? He'll get root k. So why not take k square only initially? Root of it will come as root of p. Yes, yes. There is a reason for that. Okay, we will see later. Okay? Without reason, these kind of things will not come.